Hello, my name is Fironan and today I'm going to talk about our topic quantum transport simulation with the first order perturbation, intrinsic AC performance of extremely scaled nanosheet MOSFETs in terahertz frequencies. The outline of our work is introduced here. First, we are going to talk about the introduction and the motivation of our work, and then the procedure of our work for two-dimensional double gate FET will be explained under DC simulation. The first order perturbation will be applied and the following results will be shown. The method will be extended to the three-dimensional nanosheet case and the results of the AC simulation will be shown. Lastly, we will conclude our work. First, non-equilibrium Green's function is one of the standard quantum transport simulation methods, especially for evaluating the nanoscaled transistors. NEGF is nowadays widely adopted, as you can see in the right picture. It is a figure on the usage of a certain NEGF simulation tool in NanoHub. We can find that the tool is used worldwide. Moreover, there are more NEGF tools which can be easily found on the site. However, most of these NEGF simulations have been only used to cover the DC simulation. In contrast, TCAD tools are already fully capable of transient and AC simulations. Besides, BTE solvers have also become capable of transient and AC simulation to the electron devices. Even though AC NGF theory has already been well established in physics journals, it is hard to find that the theory is applied to conventional electron devices. For this reason, we are going to show the AC simulation to the nanosheet in this work. Recently, Boltzmann equation has been implemented to terahertz nanowire transistors. Below figures show the intrinsic AC performance of n-type nanowire transistor at quasi-ballistic condition. So, we are going to show the AC simulation using NGF to analyze intrinsic AC performance of a MOSFET. By including perturbed terms, we can expect the frequency domain analysis can be available, and this is our main goal for today's talk. The linearization can be implemented by relating small signal quantities. However, since the AC simulation using perturbed terms has not been tried before on conventional devices, we should check that if the equations can be implemented properly to those devices. Therefore, we are going to check the DC case by applying the first order perturbation before the AC case. By using perturbation, we can expect the improvement of the DC simulation, such as the convergence behavior, which will be introduced in the next section. So, after we show the first order perturbation is adopted to DC case properly, we will move on to the AC simulation. For reminder, what we are going to do in this section is introduced here. The equations of DC NGF are written below, as the retarded and lesser Green functions are calculated using Hamiltonian and self-energy functions. We can calculate electron density, which will be used in the Poisson solver. The Poisson equation is written below, and by solving iteratively with the DC NGF, the self-constant solution can be given as in the figure on the right. A tool in NanoHub is used for the verification of our tool. However, in today's work, we are going to convert the equations introduced in the previous slides into fully coupled forms using perturbed terms. The following red terms represent that they are in perturbed form. The Poisson equation is rewritten in another form using the response of a unit excitation of electron density at position R'. And with this response term, we can make a linearized equation as written below equation. Phi fixed contains the electrostatic potential information of dopant and gate bias consideration, and those delta n and delta phi terms are perturbed quantities which are used to update the electron density and potential. The following two slides will show perturbed NEGF equations which are slightly converted from the AC NEGF equation introduced in the reference. To calculate the perturbed lesser Green function, Red-colored functions perturbed by potential excitation at position r prime should be prepared. The retarded and advanced green function can be formed using the equation shown below. We can see that we also need a perturbed retarded context self-energy function in this equation. This step is in the next slide. The perturbed context self-energy functions are introduced here. To simplify the notation, it is expressed in two dimensions. And since the context self-energy is considered, x and z indicate the location of the contact. Especially, x is transport direction, while z is the cross-sectional direction. Their perturbation to potential at contact can be calculated using the first-order perturbation of Hamiltonian. Finally, the perturbed electron density can be calculated from the perturbed lesser green function. Two-dimensional double-gate transistor is used in this section. The geometrical information is introduced in right figure. Channel is undoped, while source and drain are doped with donors. But to ensure the good convergence, source and drain has step-like doping profile. The region closer to channel is lesser doped than high doped region, which is close to the end of the device. The real space approach is implemented, which is very general but has very slow simulation speed. The ballistic transport is assumed. Oxide penetration is neglected, and as a result, no electrons are located in oxide region. Semi-infinite lead is used for the contact consideration. The result is shown below figures. The electron density given from Gummel-Time method and coupled method are compared for both gate ramping and drain ramping cases. They showed good constancy, of course, but their convergence behavior presented differently, which will be shown in next slide. Convergence behavior is shown here. The updated electrostatic potential must be small enough to satisfy perturbation theory, and therefore, the proposed coupled method needs several pre-iterations. The coupled method is activated when the updated potential becomes lower than threshold value, as you can see in below figures. We have set the values above 1 mV, but if we select a more lower value, we can more ensure the convergence of the results. For example, in the case of drain ramping, two different threshold values were selected in the right figure. Gummel type shows linear convergence behavior requiring 50 or more iterations for updated potential to reach 10 to the minus 10. However, the fully coupled scheme needs only 10 to 20 iterations, including pre-iteration step, and quadratic convergence behavior can be clearly observed. To see the difference between two schemes more in detail, the potential update along the midline of the device is presented in below during gate ramping and drain ramping cases. The coupled scheme result is given from the first iteration when the scheme is activated. For example, in the left figure, after 4 Gummel type iterations, the fully coupled scheme is activated. The fully coupled method shows larger updated potential than the Gummel type method. We have shown that the proposed method has good agreement with Gummel type method. Moreover, even though the calculation system becomes more burden, quadratic convergence behavior has been achieved and iteration step greatly reduced. The important thing is that the perturbed terms introduced in the previous slides can be used to do AC analysis. From now on, three-dimensional nanosFET is going to be used for the following simulations. AC energy equations are introduced below. The ballistic transport is understood, and a small signal with frequency omega and amplitude V amp is applied to a contact. The AC retarded and advanced green function equations are shown below, and they consist of both DC terms and AC terms. Therefore, we should assume that the DC results are already given for the AC simulation. But it should be noted that some of using terms are given from the different energy. The rest of the equations are introduced here. AC Lesser-Green's function equation is quite long, but can be obtained easily with the terms obtained from previous slides. Using these terms, we can calculate AC electron density, which is used in the AC Poisson equation to obtain a self-constant solution. Also, in this AC NGF simulation, we implemented a coupled scheme to obtain the solution. Both real part and imaginary part of potential and electron density are fully accounted. To implement the coupled scheme, the AC electron density is separated into two parts. The F subscripted with a large V is related to AC potential, and the F subscripted with a small v is related to small signal amplitude. The process to obtain these values is in the next slide. So the terms are converted to the perturbed terms by unit excitation. AC Green functions and AC contact self-energy functions due to the perturbation is shown in this slide. Finally, the equation for particle current calculation is shown. This equation also looks very complicated, but it can be calculated by just placing the terms to the right position. When the displacement current is calculated, the terminal AC current can be given by summing these two currents at each terminal. However, it should be noted that the total current obtained from summing all the terminal AC current should be zero. It means that the current conservation must be satisfied. For the implementation, our in-house simulator G device is used. As you can see, it has its own grammar, and the figures below are results of previous research using this tool. The device information is introduced here. Gate work function is chosen 4.3 electron volt, and geometric information is shown in the figure. Drain and source are doped with donor. Channel is also doped with donor, but lesser amount. The coupled mode space approach is adopted in this work, and other assumptions are same as the previous section. The result of the sub-end profile along the channel direction is also shown. The comparison between real space and mode space approach in DC level is presented before going on to the AC simulation. Only in this slide, a shorter width device with a small amount of mesh nodes is used to reduce time consumption. As you can see, they show good agreement, and the coupled mode space approach can be understood. Also, in this slide, the DC result from the coupled mode space approach is shown. In the right top two figures, the result from considering 5 modes is drawn in solid line, while 8 mode case is represented by symbols. The result considering 5 modes and 8 modes at each valley has no difference, so it can be seen that consideration of 5 modes is sufficient. The DC input and output curves are shown in left bottom figures. For the verification of our tool, a certain tool in NanoHub is used for comparison and showed good consistency. From the next slide, the AC simulation will be shown. As you can see from the equation written below, the AC NGF can be simulated only at discrete frequencies. For example, the DC Green's function and self-energy function at energy E plus half omega are necessary to obtain AC terms. Therefore, the energy spacing for DC NGF calculation can be related with the half omega by setting two quantities the same. For example, energy spacing 0.2 mV corresponds to AC simulation at 48 GHz. As a result, simulation at low frequency requires extremely fine energy spacing, but this is limited by memory and time consumption. However, even with these limitations, the simulation at low frequency range is necessary to compare the quasi-static result for the verification. So, to compare with the quasi-static result, AC NGF results are calculated at low frequency. On the low frequency limit, gate to drain admittance can converge into transconductance. Similarly, drain-to-drain admittance has a reciprocal relation with the output resistance. The result below shows the result of transconductance and output resistance for gate biases. The solid line presents the result from DC-NGF, while the symboled ones are obtained from AC-NGF. To obtain the transconductance and output resistance from DC-NGF, these results are calculated by taking the finite difference between two neighboring bias points. The results calculated from DC-NGF show good consistency with the AC-NGF result. The one-dimensional electron density along the channel is shown for gate and drain excitation cases under non-equilibrium conditions. Also, in this slide, the results from AC-NGF results are compared with the quasi-static results from DC-NGF and exhibits good consistency. More response of one-dimensional electron density to gate excitation is presented in this slide as several DC gate biases. Left is from equilibrium condition, while the right one is from non-equilibrium condition. The current conservation is shown in this slide. To generalize the result, Y parameters are shown instead of the current. The Y parameter at each terminal is shown below figures when the small signal is applied to the gate. The right top figures are obtained when bias is fixed, while the left bottom figures are obtained when the frequency is fixed to 10 THz. As you can see, the total summation of Y parameters is 0 no matter of conditions. The result shows the satisfaction of the current conservation. The figure shows the frequency dependent of the Y parameter under non-equilibrium condition. Frequency range 50 GHz to 10 THz is shown. The result is constant with the intrinsic equation written below. The imaginary part increases linearly since it is dependent on frequency. At low frequency range, the real part of admittance is almost the same as the transconductance as shown in the right top figure. The amount is about 64 microampere volt and 108 microampere per volt. The real part of admittance starts to drop drastically near cutoff frequency. The magnitude of admittance is shown on the right figure. Both drain and gate excitation are shown. Source terminal is not drawn here since we have verified the current conservation and therefore source term can be simply estimated. Similar shape with Boltzmann calculation is obtained as you can see on the left bottom figure which have been shown previously. Admittances appear linearly as frequency increases. The reason is that at intrinsic Y parameter network, admittance is linearly dependent on frequency when frequency terms become dominant. The results show good consistency with the Y parameter equations of intrinsic small signal model introduced in the reference. In this slide, the effort to obtain the cutoff frequency is presented. We obtain the cutoff frequency when the gate to drain small signal current gain becomes 1. For example, in the left figure, small signal current gain becomes 1 nearly at 3 THz. On the right figure, cutoff frequency is drawn as several gate biases when drain voltage is 0.3 volt. The result is obtained by extrapolating the small signal current gain by assuming that the small signal current gain appears linearly before cutoff frequency as in the left figure. As a result, when gate bias is 0.4 volt, the cutoff frequency appeared nearly at 3 THz as we told in left figure. However, values are too high exceeding 1 THz and still increases at higher gate biases. The reason is that we have a theoretical limit of ballistic transport, and in order to go over this limitation, scattering effect must be added to the system. Let me conclude my talk. We have shown the equations using the first order perturbation, and the equations in coupled form are implemented to solve NGF with the Poisson equation simultaneously. Using these equations, we have achieved quadratic convergence and shown improvement of convergence behavior in DC simulation. Then, we have shown the AC simulation for 3-dimensional nanosheet and verified that our results have good consistency with the quasi-static result at low frequency. We showed that current is conserved at several different conditions and frequency dependence of admittance has been presented. Finally, the cutoff frequency is obtained by frequency analysis at intrinsic level. However, the method should be extended to coupled mode space approach to evaluate more general devices that the decoupled mode space approach cannot cover. For example, a device that has different cross-sections and doping profile along the channel cannot be evaluated using decoupled mode space approach. Moreover, since the scattering does not participate in this work, particular characteristics of the nanoscaled device were hard to show. If we can go beyond those limitations, it is expected that particular AC responses of the quantum transport will appear in the terahertz range. This is acknowledgement. Thank you.